Okay, so hopefully everyone can hear me, and we'll get started with this episode of the UKAEA webinar series. So my name is Chantal, and I'm a radiometric researcher in the Applied Radiation Technology Group at CCFE. As a radiometric researcher, my role basically focuses on measuring radioactivity, understanding how things become radioactive and what we can do to prevent that from happening. So my background is in physics, and I did my PhD in experimental nuclear physics before starting at CCFE just over 3 years ago. So this talk is going to provide a bit of insight into the day-to-day life of a physicist and a physicist's perspective on the role of neutrons in fusion. So please feel free to put your questions in the Q&A section as I go through the talk, and at the end we'll try to get through as many as possible. So you may be familiar with the deuterium-tritium fusion reaction from previous talks in this webinar series. The important part of this reaction for this talk is the production of neutrons. So to explain this reaction in more detail, deuterium and tritium are two types of hydrogen. The hydrogen nucleus has just a single proton. Deuterium also has a single proton, so it's part of the hydrogen family, but also has a neutron, making it a slightly heavier version of hydrogen. And tritium has a single proton and 2 neutrons, and so it's known as super heavy hydrogen. So the fusion of deuterium and tritium, which I'll refer to as DT, to produce the helium and a neutron is a favourite fusion reaction because of its potential to release huge amounts of energy. And there are lots of different types of fusion reactions we could try and do, but we choose this reaction because it has the highest probability of working at the lowest plasma temperature. So it's that sweet spot between the energy we put in and the energy gain. And when operating fusion reactors, one of the best ways to confirm that fusion reactions like DT are taking place in your reactor is to measure these neutrons, because fusion reactions do not emit light. It's not possible for us to see fusion taking place. So measuring these reactions, measuring these neutrons is a surefire way to confirm that the machine is working. However, for those who watched Chris Warwick's webinar on the history of fusion, you may remember that the early fusion reactor ITER started measuring neutrons from the reactor in 1957, leading the UK to believe that we'd cracked fusion. But unfortunately, it turned out just to be localized neutron production, not originating from fusion reactions because the fuel wasn't hot enough. We need to heat the fuel in fusion reactors to around 150 million degrees Celsius, about 10 times hotter than the center of the sun, in order for these reactions to take place. So we can't rely solely on the measurement of neutrons to confirm that fusion reactions are taking place in our reactor. We must also take other measurements like temperature as well. But neutrons are a key signature of fusion. In addition to temperature, the measurements of neutrons and the measurement of neutrons, it's also useful and important to confirm what energy the neutrons have. Because when neutrons are created in a fusion reaction, they're ejected with a specific amount of energy. And in the DT reaction, this energy is 14 MeV. So some of you will be familiar with JET, the Joint European Torus, one of the fusion devices operated at the Cunham site, and currently the world's largest operating tokamak. JET has been routinely producing neutron from fusion reactions since its construction, and notably in 1991 produced neutrons from the favoured DT reaction, and in 1997 set the world record for fusion power at 16 megawatts. With advancements in understanding and in diagnostic tools in JET, there are various ways to confirm that fusion is taking place in the reactor and to avoid the same pitfalls of Zeta. So we can confirm plasma temperature and we can detect the neutrons that are being produced. And in fact, something as simple as the cameras that are positioned to record the jet pulses often show some signs of neutron production in the tiny white flecks that appear and look a bit like static in this video footage. But we also use more sophisticated tools like fission chambers that monitor how many neutrons are being produced. Measuring the neutron energy, however, is a bit more complicated. Conventional radiation detectors use charged particles to measure the energy of radiation. But neutrons have no charge, so these conventional systems can't be used. And we have to measure neutrons by looking at how they interact with materials. And it's kind of like figuring out if it's windy outside by looking through a window. You can't see the wind, but you can see the effect it has on trees and people's hair blowing around to see how windy it is. There are various diagnostic tools that have been developed at JET to measure the energy of neutrons in this indirect way to confirm that the neutrons being produced are from fusion. So doing fusion reactions is seen as relatively trivial, but the difficulty we still face is extracting this power and putting it onto the national grid. Now, JET was never designed to provide power to the national grid. It's purely an experimental device and has provided us with a huge amount of experience teaching us how to do fusion. But to go to the next level and look at getting power from fusion devices, we turn to ITER. ITER is a fusion reactor currently under construction in the south of France. And if you're interested in seeing how a fusion reactor is built, I'd encourage you to check out the live stream of the ITER construction site, along with the ITER VR tour, which can be found on the ITER homepage. To give you an idea of just how huge ITER will be, the building will house the building that will house the ITER tokamak is around 73 meters high, about 60 meters above ground and 13 meters below ground, making it slightly taller than the Arc de Triomphe in Paris. But more excitingly, from a physics perspective, the maximum plasma volume inside the tokamak will be nearly 10 times bigger than the maximum plasma volume currently achievable in JET, which is really important for ITER to achieve all of its goals. And one of ITER's goals will be the first device to produce net plasma energy gain. The expectation is that ITER will be able to demonstrate a 10-fold energy return, or a Q factor of 10. So for every 50 megawatts of power injected into ITER to heat the plasma, 500 megawatts of fusion power will be produced for periods of 400 to 600 seconds, which will be hugely exciting and a step in the right direction. And to achieve the goals ITER is aiming for, there are several advancements in the design of the ITER tokamak compared with JET, a new technology that will move the field forward tremendously. And today I wanted to focus on one key technology in ITER known as blanket modules. ITER will be the first fusion device to test these new components. 440 modules will be installed in ITER, and they'll completely cover the inner walls of the vacuum vessel. These blanket modules are critical in shielding and protecting the vacuum vessel and ex-vessel components, with a plasma core inside the vessel at 150 million degrees and superconducting coils outside the vessel at about minus 269 degrees. These blankets have to handle what might be the most dramatic temperature gradient anywhere in the universe and protect the reactor. To help give you an idea of scale of these blankets, this figure has an average size adult walking past the central column through the center of one of these modules. Shielding will be the first major test and focus to begin with for these blanket modules in ITER. But after the initial phase and further down the line in the operation of ITER, there's a plan to modify and add to these blanket modules to test two other important operations, heating and tritium production. As neutrons have no charge, they're neutral particles, they're free to leave the plasma and radiate out towards the vacuum vessel walls. And when captured in the blanket modules, these neutrons can be used to heat water and produce tritium fuel. So to start with heating, as neutrons produced in fusion reactors are absorbed by these blanket modules, the neutrons will be slowed down and their kinetic energy will be converted into thermal energy, as well as inducing reactions in the blanket that can also heat these components. So this thermal energy will then be used to heat coolant, either helium or water in the case of ITER. And this hot coolant will be then transferred to a power cycle where steam is generated to power turbines and ultimately put power onto the national grid. ITER is still an experimental reactor and won't put any power onto the national grid, but this mechanism will be tested with an independent cooling system at ITER. Now, you might be thinking that the neutron itself is pretty small, so how can it really be responsible for generating the power that we need? Well, it's true that a single neutron or a handful of neutrons on their own won't generate much power. But in reactors like ITER and future fusion power plants, we expect to produce at least 10 to the 21 to 10 to the 22 neutrons every second. And for those who aren't familiar with scientific notation, that's upwards of this huge number, which is 1 with 21 zeros after it. So cumulatively, with this amount of neutrons being produced every second, and hopefully the vast majority are being absorbed by the blanket modules and going towards heating, the effect sums up pretty rapidly. And that's why we expect to be able to generate significant amounts of energy from these reactors. So that's heating. And I also said that later down the line in ITER operations, the blanket modules will also be responsible for tritium production. So deuterium and tritium are the key fuels for fusion reactors. And while deuterium can be extracted from seawater, the supply of tritium is limited. It's estimated currently at about 20 kilos. ITER will procure the tritium fuel necessary for its expected 20-year lifetime from the global inventory, but future fusion power plants will need about 300 grams of tritium per day. And there's no sufficient external source of tritium that currently exists for fusion energy development beyond ITER. So it makes the successful development of tritium breeding essential for the future of fusion energy. The testing of mock-up in-vessel tritium breeding blankets is a mission for one of the later stages of ITER's operation and hugely important for demonstrating fusion's potential as a viable future energy source. This mechanism is achieved by introducing lithium into these blanket modules. So neutrons absorbed by the blankets will collide with the lithium it contains, and this reaction produces tritium and helium. The tritium can then be collected and pumped back into the reactor to fuse with deuterium, and the idea is that this creates a self-sufficient cycle. The design of ITER is a huge international collaborative effort, and there are around 35 nations involved in the ITER project. And in many ways, ITER is a fantastic example of what it really means to be a scientist. Fusion energy has the potential to solve the world's energy crisis. And rather than everyone competing with each other, nations from around the world are working together to solve this challenge. And lessons learned from ITER will then be taken back to each of these countries so that everyone around the world can learn together and build future fusion power plants that we're working towards. Even in the design of the blanket modules, there are several design concepts, and recently 6 were selected by the ITER module program committee to be tested when ITER is operational. 2 of the designs came from the EU, 1 came from Japan, another from Korea and China, and also from India. And so the next question is, do any of these designs work as we expect them to? Which one works the best? And hopefully 1 or more of these designs will be good enough to be the blanket module design used in future power plants. So hopefully by now you know the importance of neutrons, and that's a bit more clear. Neutrons are key indicators that fusion reactions are taking place, and by interacting with blanket modules, neutrons can provide tritium to keep fueling the reactor and also generate heat to power turbines and put power onto the national grid. But neutrons are not all good. As I mentioned earlier, ITER is expected to produce about 10 to the 21 neutrons every second, and these billions of neutrons are flying around in every possible direction, colliding with anything in their path. Ideally, most of these neutrons will hit the blanket modules, generate tritium and power the grid, but many neutrons will also collide with the steel, tungsten, beryllium, and any other material used to construct the reactor. All of these structural materials are themselves made up of atoms, the tiny building blocks that make up everything around us. And when these materials are hit by neutrons, what actually happens is the atoms that make up the materials are hit by the neutrons. And when that happens, it changes the material and makes it radioactive in a process known as transmutation. So iron, for example, is present in steel, and the neutron hits the iron, it changes the iron nucleus into manganese nucleus, and a proton and a gamma ray are emitted. The gamma ray is a packet of energy, like visible light photons, but much higher in frequency on the electromagnetic spectrum that you may have learned about at school. So that the neutrons turn the iron in metal into something that emits gamma rays. And in this example, radioactive manganese created inside the metal will remain radioactive and keep emitting gamma rays for hundreds of days. As a radiometric researcher, I'm interested in understanding how different materials inside the fusion reactor become radioactive. Fusion power is, of course, a green energy source in that it doesn't release any carbon dioxide into the atmosphere, and has loads of other benefits, including an abundant source of fuel, and it's a safe and continuous supply of energy. In terms of the radioactive waste produced, the fusion reaction itself doesn't create any radioactive waste as such. The waste product from the DT reaction, for example, is helium, which is non-radioactive. However, structural material can become radioactive as the fusion reactor is used. Firstly, the tritium fuel itself is radioactive, and some of that will be absorbed into the structure of the fusion reactor. But also, with all these neutrons flying around inside the reactor, some of them will collide with the structural material and make it radioactive. The activity of structural components in fusion will last at most a few thousand years. And when compared with the waste from fission, our current nuclear power source, not only does the radioactive waste from fission last a lot longer, up to 100,000 years, but it's also highly active and highly toxic. Spent fuel makes it really difficult to manage and store. So the waste produced from fusion will still need to be managed appropriately, but it will be much easier to handle and process. And as far as possible, we'll be minimizing the waste produced by choosing low activation materials for construction. And this is one of the key reasons why fusion is the preferred nuclear option to complement energy production from solar and wind farms. So by understanding how different materials in a fusion reactor become radioactive, a lot of my work is then focused on comparing this information with predictions from simulations. Basically, I'm interested in determining how good our computer-based models are for fusion reactors by seeing how good they are at predicting radioactivity. This work's important for a lot of reasons, but primarily, if we can rely on our models and our predictions, then before we even build a fusion power plant, we can calculate how much radioactive waste will be produced. And when we come to decommission the power plant, before we build the reactor, we can identify what part of the reactor or what kinds of materials contribute most to the radioactive waste predicted, and look at ways of either not including those materials or using less of them, or at least having a plan for how best to decommission the reactor in the future. And up until fairly recently, these simulations only really focused on structural materials in devices like JET and ITER. And being structural materials, they're static. They don't move until the machine is decommissioned. But in all of these fusion devices, there are also fluids circulating around the device, and these can also become radioactive. Flowing water, for example, is used to keep components cool and prevent them from overheating. In the blanket modules, cooling water is run to and from the shield blocks to remove the high heat load on these components, and in the diverter, as the energetic plasma particles strike the targets and that kinetic energy is transformed into heat, the heat is managed by the active cooling water system. And these cooling water systems go all around ITER. And this diagram is a computer-generated model, a computer-generated picture of ITER, where everything on the machine has been made transparent, apart from the water pipes. So you can see just how many there are in this highly complex system. The water cooling system is playing a really important role, cooling components in the reactor. But with all of those neutrons flying around, this water can also become radioactive, just like the structural materials like steel. The main challenge here is that the water is constantly moving around these different loops with branches and tanks. So we now have a moving source of radioactivity that can leave the vessel and pass by sensitive equipment or pass near operators where people are working. So it's important that we understand how radioactive the water will get so that we can put in appropriate shielding and protection to make sure that sensitive equipment is not damaged and that the people working in these reactors are safe. To test our ability to simulate and predict the radioactivity of water inside fusion reactors, I was recently involved in an experiment in Italy at a lab in Frascati, which is just outside Rome. And as you can see, I had a very pleasant couple of weeks there. This picture shows the device we used in our experiment, and it's known as the Frascati neutron generator. So deuterium is accelerated down this section, and it collides with the tritium target to produce neutrons with the same energy as they would be produced in a fusion device like JET and ITER, because it's the same DT reaction. This device produces around 10 to the 10 neutrons per second. We placed a simple water circuit at the end in front of the source of neutrons to allow it to become radioactive in the same way it would in a machine like JET. And coming out of the back of this water circuit are two tubes. So water becomes radioactive here. It then leaves the component and follows the tube round to a radiation detector where we measure how radioactive the water is. And then the water goes into another tube and comes back to this component to get irradiated again. So in this way, we can keep collecting data as the water flows around the circuit. And what we measured with our radiation detector is nitrogen-16 and nitrogen-17. So the oxygen in the water had transmutated and produced these two nitrogen isotopes that are radioactive and emit gamma rays. Nitrogen-17 also emits neutrons. When we compared this to our computer models, we found that we got an agreement within 10% or so. So the experimental and calculated results nearly matched, but there were some differences. And so my work at the moment focuses on how we can improve these calculations to get a better agreement with the experimental data. And then the next step will be to look at how much more complex systems like ITER's water cooling system rather than a simple circuit like this. So for my final slide, it wouldn't be a talk about neutrons without mentioning aneutronic fusion. And I apologize if this was someone's question that I'm already going to answer. Some of you might be thinking that the problematic side of neutrons is that they damage things and make materials radioactive in the reactor. So why not abandon the DT reactions and instead do fusion reactions that don't produce neutrons? And indeed, there are several types of fusion reactions that don't produce any neutrons, and these are collectively known as aneutronic fusion reactions, allowing you, in theory, to get all the benefits of fusion with none of the negative parts. However, there's one big reason why at the moment this is not considered a viable way of achieving fusion power in the foreseeable future. It's really hard to do aneutronic fusion. Doing regular DT fusion is hard enough. You have to heat your fuel to 10 times hotter than the center of the sun, 150 million degrees. But for aneutronic fusion, you would need to heat your fuel to billions of degrees. For example, this particular aneutronic reaction needs the fuel to be heated to 3 billion degrees. This doesn't mean it's not being looked into. However, there's actually a lab in America, TAE Technologies, formerly known as Trialpha Energy, whose aim is to do this proton-boron 11 reaction to produce 3 helium products. Now this diagram is a slightly simplified version of the process, but what it highlights is that the fuel is readily available and non-radioactive, and what it produces is 3 helium products, which again are inert, they're not radioactive. We get no neutrons being produced. It's largely been proven that this kind of fusion reaction can't be done in a conventional tokamak like JET and ITER. So TAE have had to design a different type of fusion device, this long cigar-shaped fusion device. But at the moment, due to the relative success of devices like JET, aneutronic fusion is not seen as a mainstream way that fusion will be achieved in the near future, and so DT fusion in tokamaks based on JET and ITER are still favoured. And in fact, it was recently reported that TAE managed to achieve temperatures of around 10 million degrees in their reactors, so there's still quite a long way before they reach these 3 billion degrees that they need. So there's a way to go in the research, yeah. And that brings me to the end of my presentation about neutrons and fusion. To find out more information, I encourage you to go to these websites and follow us on social media. But I think now we can maybe have a look at some questions. And I will just ask Emily if she can bring up some questions for me, if that's okay.
Hiya. So there aren't any questions in the Q&A box at the moment. But if anyone would like to ask, then yeah, now's a good time.
I guess we could maybe release the poll now, and I can explain a bit about that. So this presentation I gave today was very much a general overview of neutrons in fusion, and some sort of touching on some of the research that I'm doing at the moment. And so our poll today is really to assess from you, whether there would be any appetite for a more detailed and in-depth version of this talk that goes into some of the kind of nitty-gritty science aspects. So if I open that, feel free to leave your response to what you'd like. So I will leave that running. So I think we've got a few questions coming now. So let's have a look. Well, there's a very easy one that's come up. Is a recording of this going to go onto the YouTube channel? That's a yes. Yeah, this presentation is being recorded, and so that will be shared on social media. Thank you very much for the talk. How did you get involved with fusion research? So, as I said, my background is in physics. I did my PhD at the University of Brighton in experimental nuclear physics, and my PhD itself was quite a lot different to the type of research that I'm doing now. So when I was doing my PhD, I was looking at, I travelled a lot to labs in Finland, trying to create exotic nuclei, exotic yttrium nuclei that don't exist on Earth, and understand how these things decay. And it was really interesting research, but I think throughout the course of my PhD, I was very keen to become more involved in the applications of scientific research, rather than focusing sort of more heavily on the kind of data side of it. So I came across on sort of by chance really a job advert for CCFE, and I'd already always had an interest in fusion. Yeah, I guess the right job came along at the right time, and was successful in getting that. So it certainly helped to have that physics background and to have that interest in fusion. But I think if you're interested in pursuing a career in fusion research, now is a really good time. And actually, I think the talk next week will actually be about recruitment. So I'd encourage you actually to tune into that one, and maybe you'll get some pointers. Okay, what else have we got? How is the neutron yield measured at JET, and which diagnostic is used? So I'm not involved myself too heavily with all of the different diagnostic systems on JET. And I think, again, there's actually going to be a talk in a few weeks on JET diagnostic tools. So I encourage you to look out for that one. It'll give you a much deeper explanation. But I think primarily for measuring the neutron yield, I think fission chambers are primarily used on JET. So yeah, check out that talk for some more details on that. What else have we got? When do you think nuclear fusion will be a common source of energy? Well, yeah, this is the classic question that everyone likes to ask. It's really, really difficult to put a timeline on it, really. The general roadmap of fusion, at least in Europe, different countries around the world, different nations around the world have their own version of the fusion roadmap. But in Europe, at least, the ITER, we hope will be operational within the next couple of years or so. And then assuming that the ITER program sort of produces all the results that we want to see, one of the key outputs of ITER is that it has to demonstrate it can get net plasma energy gain, and that all of these new components that we know we're going to need in fusion reactors and fusion power plants, they will have to work, and we have to find a way of making those work. And once we reach those milestones, we can then start to really understand what a future power plant is going to look like. But the plan is that we have another device to follow ITER, and that will be demo, and that will be operational around 2050. So the current so demo will be a demonstration power plant, and so at that point, that's when we'll really be able to see that fusion's within reaching distance. So it's that sort of roughly 30 years or so before we're really at the point of thinking about what fusion power plants will look like. But what's really exciting at the moment in the UK's fusion programme, so that's very much the European plan, but in the UK, you may have heard recently of the announcement of STEP, which is the UK's sort of new fusion device that's it's currently going through the conceptual stage, and that's really going to advance the UK's programme on working out, our path to getting towards these fusion power plants. So I encourage you to have a look a bit more online about STEP as well. Okay, lots of thank yous. That's great. Thanks. Okay, so what about the helium product of DT reaction? How is it used and where does the helium go? So the helium that we produce in JET at the moment, JET's the only reactor that's doing this DT reaction to produce any significant amounts of helium. At the moment, that's not being used at all. So when we have our deuterium and tritium fusing in the plasma, they'll produce neutrons and helium. And at the moment, it's first of all very important that that helium is extracted from the plasma through the diverter. We don't want helium staying in the plasma because it's really hard to maintain these high plasma temperatures if you've got loads of helium contamination in there. So the helium is extracted from the plasma using the diverter. And then really essentially it's just sort of clean, filtered. We have to make sure there's no sort of tritium in there, things like that. And we just don't use the helium for anything. In JET, there's not really a lot of helium produced. So we have a few campaigns. We have a campaign that will be starting hopefully again soon once we can all get back to work. But we run, say, like a campaign a year with sort of like 20 or so shots a day that run for about a second each. So we're not really producing a lot of helium when we're running JET, so it's not really worth trying to collect up that helium and use it for anything. ITER will be very much the same sort of deal. So in both of these machines, although they're both capable of doing this deuterium-tritium reaction, they won't be doing it all the time because tritium's quite hard to get hold of. But in future fusion power plants, I think there are some people that are thinking how we can best use this helium that's being produced. Helium is a limited resource on Earth, so we don't really want to, if we can collect it and use it for something, that would be fantastic. But I think certainly for the time being, it's not really seen as something that's kind of worth trying to do. There's not really a lot of it that's produced. Okay. So is it possible to take radioactivity out of fluids like water once they've been exposed to neutrons? So Essentially not really, although I'll explain some ideas along that line of thinking in a minute. But really when, for the case of any fluid, I mentioned water, but there's lots of other fluids that will become radioactive in a fusion reactor. When the fluid becomes radioactive, pretty much all of it's radioactive because the fluid's quite turbulent, and so any atoms inside that are radioactive, they're all going to be mixed around, and so really you have to consider it as the whole volume being radioactive. Now, two isotopes that we identified as becoming radioactive in water, they only last for a few seconds, so it's not really worth trying to extract them in any way to take the radioactivity out of water. All you need is a tank and to leave it in there for a few minutes, and then all of your radioactivity is gone, it's decayed away. But for longer lived radioactivity in materials, primarily I'm thinking about steels. When steel becomes radioactive, there's lots of components in there that will last for, say, up to 1,000 years. And there are some people that are, and equipment that we can use to identify hotspots in these materials. So rather than having to sort of store a huge sheet of steel, we can just take out the kind of hotspots of these bits of steel that have the most radioactivity in them, and keep them in high sort of storage facilities. And not have to worry about all of the material as a bulk. So something along those lines it is considered, yeah. Okay. Will jet continue once ITER's running? I mean, it's difficult to say, but what, jet was never supposed to run for as long as it has done. It's already far extended its sort of operational expectation. So to keep jet running for much longer, I think will be a challenge. It just requires so many upgrades. But there's certainly a lot of value in having at least some overlap between the operation of jet and the operation of ITER, primarily because all of the people that we've trained to use the jet device, all of that knowledge and experience will be highly useful for running ITER. So we wouldn't want there to be a big gap between the two devices. But it's certainly seen that ITER is the kind of next stage to jet. So I can't necessarily see that jet will run for very much longer after ITER is established and operational. Will helium in coolant show any effect from neutrons? Potentially. I don't know off the top of my head of any particular reactions that you have of concern between neutrons and helium. So basically, any liquids that are used inside the device have the potential to become activated by neutrons. Primarily, I've looked myself at the activation of water, but there's also other fluids that are used in the reactor as well. So for example, in some of these breeder blankets that I mentioned, lithium lead is used, liquid lithium lead, and that can become radioactive. So there's lots of different fluids inside the reactor that become activated by neutrons. Let's see. So there's a few questions in here that are more about the kind of damage of materials, neutron damage, particularly some of them are sort of neutron impact on semiconductor materials, neutron damage to the structure and the lifetime and the reliability. So neutron damage is not really my area, so I'm not going to talk about it in a huge amount of detail, but there is lots of information as the sort of links that I gave in my last slide that you can find online. But yeah, you know, neutron damage is definitely something that will happen. You know, these neutrons have relatively high energy, but there's also billions of them being produced a second. And so materials will be affected and damaged by these materials. And it's our job in my group, the sort of colleagues that I work with, you know, it's part of our job to look at how to shield components like the superconducting magnets and the vacuum vessel wall to protect these components as much as possible. But we also need facilities where we're able to test our understanding of material damage in these really extreme devices, environments that you get in fusion devices. So there's a lot of work in this area, but it's not really my area of expertise, so I won't go into it in too much detail. So once ITER's up and running at full capacity, roughly how much nuclear waste will be produced a year and how would it be stored? So I think what's quite nice to point out from this question is that for fusion reactors, really the bulk of the waste comes at the decommissioning stage. So unlike fission reactors, where you have a lot of waste coming from the actual operation of the device, in fusion, the fusion reactions don't produce any waste themselves, they just produce this helium. And then really all of the waste from fusion is in the structural materials that don't really have to be replaced very often. So there's not really going to be sort of routine annual waste produced from these devices, as I understand. And so, so yeah, it's really more at the decommissioning stage. So the thermal blankets with lithium. I'm not quite sure with this question. So how much lithium will be converted during operation? So that will actually vary. So this question is about the neutrons being absorbed by the blanket modules and converting lithium into tritium for the tritium production. And that process of how much sort of conversion, how much tritium you're producing really depends on how much you're using in your reactor. And so this is something that will fluctuate depending on how quickly the fuels are being burnt up. And it's also a way of kind of controlling the plasma. So you don't really want to burn up all your fuel really quickly. You want to sort of have this continual, gradual produce of energy. And so actually how much lithium is being sort of used and converted, that will kind of vary. But yeah, all of these components are yet to be tested, so it'd be a very interesting future goal for ITER. My understanding is that one of the consumables will be lithium. How much will be needed per megawatt generated? So per megawatt generated, it's a little bit tricky to put a number on, but the sort of analogy that I've used before is that actually the amount of lithium we need in our reactors is not a huge amount. So the sort of numbers that we try to put to this is if you take if you fill a bath with seawater and take the lithium from a phone battery, that's enough fusion fuel for one person for 7 years. So the deuterium that you'd get from a bath full of seawater and the lithium from a phone battery, converting that into tritium, that's enough fuel for one person for 7 years on sort of average energy usage. So that might give you a bit of a context into actually we don't really need a huge amount of lithium in our fusion reactor. Okay, I think I've covered pretty much all the questions now. So if we go back and have a look at the poll, so it seems that basically everyone that was in attendance today is keen for there to be a future talk that goes into a lot more detail and shows in a lot more detail the research that I've been doing. So we'll combine this with the polls that we've put out to social media and then watch this space.